All right, welcome everyone to Recovery's weekly meeting. It's been, as you can probably guess, more than a week since we had a meeting. Um, so let's get started here. Today is going to be kind of short. Most of the time is going to be just like going over all the stuff that we have done since the last meeting. So the quick overview is stuff from last week. Then we're going to talk about the progress report, and we're going to talk about the initial ground test, other updates, and then about stuff that is coming up. So from last week's, not week. So before we left off for spring break, that week we worked on the black powder system and on the bulkhead. So we put on the holder for the black powder charges. So we cut the copper caps, we drilled the hole into them. And then we also made it's not PVC, I forgot the name of this material here, but it's similar to PVC. We cut a little section of that tube so it matches the size of the black powder charges. And then we pretty much just we just used a bolt to hold it into place. So the cap there's a hole, and then we put like a nut on the other end of the bolt so we can have the cap into place. And then the tube here just slides in. And then we also made some of the charges, which you can see here. And then the parachute jig, shout out to Christian for letting us use his 3D printer. And shout out to Titus as well, because I know both of them worked on designing it on CAD, and then they printed it out. And you can see it here. We actually tested it this week when we were trying to put everything together, and I would say it works pretty good. It really helps that we can clamp it and that we can put that what do I always forget the name of these? Dowel. The dowel through the jig here. I feel like those two made it significantly better. And that kind of takes us to the next thing we did, which was, or actually before we left off, we kind of we took the weight of some of the components. And an update on that is that Ravi has asked us to update all the weights because he's trying to make make better simulations. And that requires updating all the weights, because a lot of the weights that we have on there, we had to guess because in like all the websites, it didn't say how much they weighed it. So we'll be doing that next week. But then when this week, we actually tried putting all the recovery components together. And here are a couple of pictures that I took. And for those who are in there, we literally took everything that we're going to use this year for Zenith for recovery. And if we go back here, you can kind of see on this picture here how small it is. This one here, you can see that it's all really small compared to what we had for Oberon. This is a really good upgrade because it's significantly lighter and it takes significantly less space. Like for Oberon, everything just for the main parachute fit in the nose cone here. And then this year, everything for both the main and the drogue fits inside the nose cone. And then here, I just like took a picture, and everything in here, you can kind of see here the outline of where the shoulder ends, and that's kind of perfectly aligned with where the I guess the bottom of the parachute was. So everything, the recovery, all the recovery equipment goes up to like pretty much around here, like where the top of the shoulder is. And I think it's kind of hard to say, but it's like 24 inches. And then the other thing is, sorry, we've been working on the black powder and CO2 size calculator. And you can see a screenshot here, but I want to kind of go more into detail about how this works. So I'm going to exit the slides real quick, and I'm actually going to pull up the calculator. Okay. So here is the actual calculator. There is 3 different sections, as you can see here. The first one is green, the second one is like this purple, and then the third one is red one here. But starting off with the first one here, let's just do it. Shout out to Alex. He was the person who like actually put it into Excel, the first section, and then to Scott as well, because he solved a really complicated integral that we had to do to get this to work. But essentially, what we're doing with this calculator is we're taking the formula of the nose cone, which is this one here, this y equals to all of this here. And you can see it has this parameter here, which is a function of r and l. R is the radius of the nose cone, and then L is the length of the nose cone. And there's only one X here, which when I first saw this, I was like, oh, taking the integral of this is probably not that hard. But if you actually try and solve it, it's really, really complicated. So we needed somebody who's way better at math to help us out. So thank you, Scott. And once we have the integral of this here, we can use the disk method, which is where we're taking cross sections from one end of the nose cone to the other one. And we're taking that area and we're summing all of it up to get the exact volume. So once that is done, that allows us to take the exact volume of the nose cone. And then the calculator here just takes the diameter of the nose cone, the length of the nose cone, the length of the shoulder, and then the length of the distance between the bottom of the shoulder and the top of the bulkhead. So that allows us to calculate the complete volume of the recovery bay. And then we can take that volume and convert it into an equivalent cylinder here. And the reason we want to do that is because this second section here, where we're trying to calculate the amount of black powder, this formula here assumes that the recovery bay is a cylinder. So you can see here, we have the parameters of the nose cone and the layout for zenith. So 5.9 inches in diameter. The length of the nose cone is 24.68. The length of the shoulder is 6. And right now with the design we have for zenith, the bulkhead is going to be flush with the bottom of the shoulder. So this is going to be 0. And then here, this is a radius. This is the P value here, or I guess rho. And then this is the volume of the nose cone, which comes from that integral here. And here's a picture of the solution. Yeah, this here. This really complicated formula. So that's where that comes from. And then B is the, or this is the shoulder. This is the volume of the shoulder. And then this would be the volume between the bottom of the shoulder and top of the bulkhead. And then the total volume is just adding these 3 together. And then that gives us the volume of the cylinder. But since we know the radius here, we can find the length of this equivalent cylinder here, or the height. So once we do that, we can move on to the second part here, which is calculating the amount of black powder. And if we go to this link here, it explains it. It runs you down from like, I think it starts with the ideal gas law, and it talks about black powder. And then at the end, it derives this equation here, which is how to find the amount of black powder. If you want a specific force and you have the length of your recovery bay. And in this case, since for this year, we're using shear pins, we're more interested in generating a certain force that's going to break the shear pins so we can eject the airframe, right? So we're using three 440 shear pins, which require 40 pounds each. So three of them is 120 pounds of force. And we're using a safety factor of 1.5. So I think that is 180 pounds, I think. So that's why there's a 180 pounds here. And then the length here comes from the previous section, which is this one here. So then we just plug it in into this equation, and then we get our grams of black powder, which is 1.8. For the ground test, I think we used 1.7, and the reason why there was a difference was because at the time, like these numbers here weren't updated. So now it's 1.8. And then the last section here, it just allows us to calculate the amount of moles of CO2 required to generate a specific separation pressure. And then pressure is just your force over area, right? So the force we're trying to generate here is the same as the separation force, so 180 pounds. And then the diameter is the diameter of the airframe, which is 5.9, but pressure is perpendicular to the surface, right? So if we just do 180 over 180 pounds of force over an area of pi r square, where our r is 5.9 over 2, that's assuming that the area over which this force is acting is a circle, right? But when I was looking at it today, that is incorrect, because that pressure, if it's going to be acting perpendicular to the surface here, it would mean that it would be acting perpendicular to the surface of the nose cone here, the inside surface. So we can't use pi r square, because that's not the actual area it's going to be acting over. So then what that means is that we need to find the length of this line here, so we can find the surface area of the inside of the nose cone. So the way I was thinking about doing it, but I'm not sure if this is right. If y'all like have any inputs, like let me know. But I was thinking about finding the length of this line, and then finding the surface area from there. But now that I think about it, I don't think that's right. But essentially, we need to find a way to calculate the surface area of the inside of the nose cone, and that's the actual area over which the separation force is going to be acting on. But yeah, I was thinking about finding the length of this line here, and then going from there to find the surface area. So I did some research into that, and I found this equation here that if you want to find the length of a line, if it's a function that you can find the derivative of, and it's continuous between that range you're interested on, you can use this equation here, 1 plus f prime squared, that the square root of that dx, and the integral of all of that. And the problem is that we need to take the derivative of our function, right? But if we look at our function here, it's this here, it's this whole thing here. And the problem is that you only have to take the derivative with respect to x, right? But x is under this square term, which itself is underneath this square root term. So it's actually a really difficult term to take the derivative of, which is why I was going to ask in the general chat, so somebody like Scott could help us take the derivative. But like I mentioned, I don't know if that would be the actual method of calculating the surface area of the inside of the nose cone. Um, but once we figure that out, then the calculator is going to take um, that surface area to calculate the pressure we're generating on the inside of the nose cone. And then it's going to use the ideal gas law here, N equals to PV over R times T. We're going to calculate the pressure. We have the volume, which comes from the previous section here, the total volume here of the recovery bay. And then R is the universal gas constant, and then T here. For here, in this example, they use 273 Kelvin, but they don't really explain where that number comes from. But I think for now, we can just assume that this is right, but definitely in the future, I think it would be really helpful to understand where exactly they're getting this number from. And then the last input is the molecular weight of CO2, which is 44. So then what you do is you find the number of moles here, which is what I said earlier. Where is it? PV over R over T. So this is the number of moles. And then from that, you just multiply times the molecular weight to get your grams of CO2. So I don't know how big of a difference it's going to make whenever we actually find the surface area of the inside of the nose cone. But right now we have that we would require 7.6 grams of CO2 to generate the 180 pounds of force required to eject the airframe. So they do have 8 grams, 8 gram CO2 cartridges, but I mean, I guess we'll test it out, but I think we should probably go with 16 because right here it says that you want to use like a additional 20%, right? So if we do this times 1.2 is going to be over 8 grams, which means we need to go to the next size of CO2 cartridges, which I think are going to be the 16 gram ones. Okay, let's go back to the meeting now. Let's see, where were we? Right here. So that's all of that for the calculator. And then the progress report, I mean, this was before spring break. So an update on the progress report, most of the sections are done. There is still some sections that need a little rework. I haven't had the time this week to message some of the members who worked on those sections that need a little bit of rework. But I will try to finish it. It doesn't require that much work. And the reason why I want to make sure that we do a good job with the progress report is because whenever we do write the final report for Spaceport, you know, looking back at the documentation we worked on over the year is really going to help us with the final report. So there's not much to say about that. And then this is the same slide from the weekly update, but for the ground test, we had the procedures are here if you want to look at them. Recovery didn't have any issues. I think it was excellent. The assembly was fast, it was easy, and we didn't run into any issues. And I know I feel like I feel more confident now about going to competition and having to assemble all of this. Unfortunately, avionics ran into some issues with the telemetrum, so we weren't actually able to set off any of the different systems. But as soon as they figure that out, I would like to reschedule it as soon as possible. And I mean, the CD3, it's ready to go. So all we will have to do is kind of just clamp it like we have it here and then ignite it with the E-match. Same for the black powder charges, those are ready to go. And then the tender descenders, we disarmed them on Wednesday. because we were trying to put everything together, but the tender descender assembly is like really, really simple. So that shouldn't take too long. Other updates, let's see. So the plan for testing the main parachute and the drogue is to just attach a weight to them and then drop them from a known height. The procedures for the drogue are finished already, and then I'll work on the main ones, but the procedures for the drogue and the main are going to be really, really similar. The only difference is that for the main, we are going to be kind of giving it way more space because it's a bigger parachute. So for the drogue, we're planning on going to a building like Agnes Arnold and maybe just dropping it from like the first floor or the second floor, because there is like a basement floor. And then we are going to record it, and cameras record at a certain interval, like it's like the frames per second, so it's how many pictures it's taking per second or whatever. So if we take that and the number of frames, we can take the amount of time that it took for the parachute to land, and since we know the distance and we know the time, we can take the average velocity that it took for it to land, and we can compare that average descent rate and compare it to the calculator that we have. So if they're similar to each other, then we can confirm that the coefficient of drag is what it says on the website. And then analysis is working on a CAD of the bulkhead. I don't know if I said that on the previous meeting, but they are working on it. So one of these days we'll have a really nice CAD of the bulkhead. And finally, upcoming, we're going to try to figure out the inside surface area of the nose cone. We're gonna weigh all the components. That's what we'll do on Monday, I think, as well as practicing the flaking and figure-8 knots. And then on Wednesday, there were some requests to push back the parachute test to Wednesday. So that's what we'll do next week. Is there any questions?
Can I get the amount we have right now?
No questions. All right. Well, and that is it for this week. If you have any questions or comments or feedback, feel free to send me a message on Discord. I'm always free. And thank you to all the members for all the hard work. All right, I'll catch y'all later. Please stop the recording.